Have you ever wondered if the universe itself holds a doorway through time, a way to step beyond the moment we live in? The night feels alive, almost as if time is breathing beside you. So before sleep finds you, let's drift through galaxies and light, through space-time itself, to ask the question that has always haunted us. Is time travel possible in our universe? Time is the one thing you can never hold in your hand, but somehow it holds everything. It wraps around you, runs through you. It marks your days, your years, your life. You live inside it, every heartbeat, every breath, every memory soaked in its rhythm. And yet, we don't really know what it is, do we? We measure it, sure, we count it with clocks, with calendars, with numbers that tick and flip, but that's not time itself. That's like looking at a thermometer and thinking you understand heat. Time is stranger than we've been told, far more powerful than we imagine. So let's pull back the curtain a little. What is time really? Is it a river, a direction, a dimension, or something else entirely? Can you move through it, maybe even jump ahead? And the answer, well, science says yes, in a way. If you move fast enough, close to the speed of light, you can travel into the future. That's not science fiction, that's physics. The hard part isn't the how, it's the how much, the scale, the speed. But the real madness starts when we look backward, the past. Can we ever go back? Can we visit a moment that's already happened? Some scientists whisper about wormholes, shortcuts through space-time, little tunnels that could connect one instant to another. Others warn about paradoxes, contradictions that could tear logic apart, unravel everything. And at the far edge of all that, at the border where equations break and physics trembles, time itself begins to come undone. It stretches, bends, maybe even loops back on itself. That's where the idea of a time machine stops being a fantasy and starts becoming a question, a mirror held up to the universe, asking, what are you really made of? So yeah, take a look at your clock, listen to that ticking sound, because by the end of this, you won't hear it the same way again. We live with time every day, but we rarely stop to feel it. It governs everything, our routines, our aging, the slow drift of the stars. It feels steady, like a river pushing us forward. But is it really flowing, or are we the ones moving through it? At first, it seems simple. Time is what clocks measure, what calendars keep. You wake up, work, eat, sleep. The hands keep turning, the days keep changing. It's 3:15 when you check your watch, Tuesday when you plan a meeting. That's the structure we lean on, but physics says time isn't separate. It's not this independent thing ticking in the background. It's tied to space, woven into it. Space and time are one fabric space-time. Picture it, an invisible sheet stretching endlessly, holding everything, every star, every galaxy, every beam of light. Not just where things are, but when they are. That's space-time, the stage and the story, all at once. Einstein showed us that. Before him, we thought time was absolute, ticking the same for everyone, everywhere, forever, but it's not. It bends, it stretches, it curves with matter and energy. Gravity itself isn't a pull, it's the bending of that fabric. So when you think of time now, don't picture a clock. Picture a vast living field, rippling with stars, folding under the weight of planets, expanding with the universe. That's time. Not a thing outside you, but the thing you are swimming in, always moving, always part of it. So for a long time, people thought of space as this kind of fixed stage, like a giant backdrop where the whole drama of the universe just played out and nothing ever happened to the stage itself. It was solid, still unchanging, and then Einstein came along and just tore that picture apart completely. He said, no, space and time, they're not fixed, they're alive, they can stretch, they can bend, they can ripple. They respond to the presence of matter and energy as if the universe itself were breathing and shifting under its own weight. And that idea, it's wild because it means gravity isn't really a force, not in the way we were taught. It's geometry, it's shape. Imagine laying out a rubber sheet flat across a table. That's your space-time, smooth, calm. And then you drop something heavy in the middle, a bowling ball, a star, and the sheet dips curves under the weight. Now roll a smaller ball nearby. It starts to spiral inward, not because there's an invisible rope pulling it, but because the surface itself is bent. That's how Einstein saw gravity, not a mysterious pull, but the natural path through curved space-time. Massive objects bend the fabric, and everything else just follows the curves. It's not being dragged, it's being guided by the shape of reality. And because space and time are the same fabric, when space bends, time bends too. The dip under a star slows the rhythm of seconds. The deeper the curve, the slower the tick. The time itself stretched and twisted by the same geometry that shapes planets and orbits. And that's where things start to get strange, because in Einstein's equations, there's no built-in sense of past or future. Those are human words, convenient but not fundamental. The math doesn't say this is yesterday and that is tomorrow. It just describes how the fabric behaves, how it folds and warps as energy moves through it. Time becomes a dimension like any other one. You can map not just where something is, but when it is 3 coordinates for space 1, for time, all woven together into a single 4-dimensional tapestry. And here's the curious part. While you can move freely through space, left, right, up, down in time, it feels different, one direction, only forward. But in the equations, all of time already exists. Every moment, past, present, future, all part of the same structure, laid out like a landscape. And that leads to a strange thought. Maybe time doesn't flow. Maybe it just is like all places already exist. Maybe all moments do too. We just experience them one at a time, moving through a pattern that's already there. Einstein once said the distinction between past, present, and future is only a stubbornly persistent illusion. He didn't mean time isn't real. He meant that the flow we feel might be something our minds create, a kind of story stitched over a timeless geometry. And that's unsettling, isn't it? Because if physics doesn't choose one moment over another, why does it feel like the world is always moving forward? Why do broken cups stay broken? Why do we remember the past but never the future? Maybe the arrow of time isn't written in the universe. Maybe it's written in us, in the way we remember, the way we change, the way entropy drags everything one way and never back. And in that sense, the ticking of time might just be the sound of the cosmos rearranging itself into memory. This puzzle, it's one of the strangest in physics. The arrow of time, Einstein's equations, they don't give it special treatment. To them, time is just another direction, no more important than left or right, forward or back. But that's not how we live it, right? Because to us, time feels like it moves, it flows, always forward, never back. We're born, we grow, we age, we fade. You light a match, it burns, it becomes ash, and no matter how much you want, you can't make it unburn. The world seems built to move one way. And to understand that, physicists don't look at gravity or relativity. They look at heat, they look at energy, thermodynamics. The second law, it says that in any closed system, entropy, the measure of disorder, always increases. Always. It's not a suggestion, it's a rule. The universe's quiet rule of decay. Things go from order to chaos, from structured to scattered. You drop an egg, it shatters. The shell breaks, the yolk spills, and no force on earth will pull it back together again. Not because it's impossible, but because it's so wildly, astronomically unlikely that it may as well be. That one-way slide from order to disorder, that's the arrow of time, and it's everywhere. In melting ice, in fading stars, in the cooling of the cosmos itself. Entropy grows, and in doing so, it gives us the feeling of before and after, of cause and effect, of a story that only moves one direction. But the equations underneath, the ones describing all this, they don't care which way time runs. Run them backward, they still work. So in a sense, every moment, past, present, future, exists together like pages in a book. You read from the front to the back, but all the pages are there all at once. Entropy is what makes the story feel like it's moving. It's why when you watch a glass fall and smash and then see the film in reverse, it feels wrong, unnatural. Because that would mean entropy going backward, and nature just doesn't do that. So time, as we feel it, as we live it, is an illusion of arrangement, of probability. The universe itself isn't forcing the arrow, it's just playing the odds. That's why physicists say the present isn't unique, that the future isn't sealed off, that the past never fully disappears. They're all part of the same vast fabric, stitched together by chance and heat and entropy. And to really see how deep that goes, we have to ask the impossible. If time can bend, if it can stretch, if entropy gives it direction, could we ever move through it? Not in thought, but in truth. When Russian cosmonaut Sergei Krikalev came back to Earth in October 2005, he wasn't just an astronaut returning home, he was a traveler who had literally moved through time. 6 missions, nearly 2 decades, more than 800 days circling the planet, watching the sun rise and set 16 times a day. From orbit, he'd lived slower. His clock had ticked fewer times. Einstein predicted it, and the universe confirmed it. He came home younger than if he'd stayed, not by much, fractions of a second, but still real. Proof that time isn't rigid. It can bend, it can stretch, it can be touched, even if you can't hold it. So there's this man, right? And his story is just wild. His career began back in the Cold War era, 1988, when he launched aboard the Soviet Soyuz TM-7 mission. Imagine that moment, a world split in two, both sides racing toward the stars, and he's up there, rising through the atmosphere into orbit. He worked on the Mir space station, which at the time was the crown jewel of Soviet space exploration, this shining symbol of human endurance hanging in the dark. And he didn't just visit once, he kept going back, returning again and again to that floating laboratory, living and working in microgravity for months at a time. No gravity, no solid ground, just endless orbit. He became known for his calm under pressure, his precision, his quiet courage, his willingness to stay out there far from home for as long as it took. There was this one mission in 1991 that turned surreal. While he was orbiting Earth, the Soviet Union collapsed. It dissolved beneath him. Imagine that, circling a planet that suddenly no longer had the same countries it did when you left. He went up a Soviet citizen and came back something else, from a nation that didn't exist anymore. Later, when the space age shifted from rivalry to cooperation, he joined NASA astronauts aboard the space shuttle and became part of the International Space Station program. He flew on the very first expedition to the ISS in 2000 and then returned in 2005 for a 6th mission, this time as a seasoned veteran. That last trip pushed his total time in space past 800 days, a world record back then. 800 days of sunrise and sunset every 90 minutes, of floating meals, of repairs, of laughter drifting through metal corridors. He lived, worked, even celebrated holidays hundreds of kilometers above the planet. But here's the part that really bends your mind. Over all those missions, he wasn't just a space traveler. He was, in a very real way, a time traveler. Yes, really. While he was in orbit, he was moving fast, incredibly fast, about 7.66 kilometers per second, roughly 27,600 kilometers per hour. And according to Einstein's special relativity, the faster you move, the slower time passes for you compared to someone standing still. So while he circled Earth, his body and his onboard clock ticked just a little more slowly than ours. Not by much, a fraction of a second, but real, measurable. Over his 803 days in orbit, that difference added up to about 20 milliseconds. Tiny, yes, but enough to say that when he landed, he was a little younger than he would have been if he'd stayed on Earth. He had literally moved through time. Not forward in the way we imagine in science fiction, but slower. He experienced time a bit more gently than we did. So when he came home, technically, he was in the future compared to the version of himself that never left. That's not metaphorical. That's physics. It's called time dilation. And it's been proven again and again. Picture this. 2 identical atomic clocks. One stays here on Earth, the other is sent up on a fast-moving satellite. When you bring them back together, they don't agree. The traveling one has ticked fewer times. Time really did move differently. It's not theory anymore. In 1971, physicists Joseph Haffel and Richard Keating flew 4 atomic clocks around the world on commercial jets. When they compared them with clocks that had stayed on the ground, the flying ones had lost time just like Einstein predicted. So when you look up and think of those astronauts orbiting the planet, remember they're not just floating above us, they're slipping, ever so slightly, into the future. So there's this equation, right? The one that actually explains why time can slow down, and it's called the time dilation formula. It comes straight from Einstein's special relativity, and yeah, it looks intimidating at first, but don't worry, you don't need to solve it, just feel what it means. In that equation, t is the time that passes for someone who's moving at a certain speed, we call it v, and t is the time for someone who's standing still, and c, that's the speed of light, the ultimate speed limit of the universe. Now here's the strange part. As v, your speed, gets closer to c, the number under that square root gets smaller, which makes the whole expression grow, and that means your time slows down, literally. The faster you go, the slower your clock ticks. You don't notice it here on Earth, because everything we do is so painfully slow compared to light, but out there, in space, it's different. A spacecraft orbiting Earth at about 28,000 kilometers per hour already feels it. Not much, just a few milliseconds lost every few months, but it's there, real, measurable. Now imagine pushing that speed all the way, almost to the speed of light, 99.9% of it. You climb aboard, you travel for what feels like a single year, you come back, and decades have passed. The people you knew are older, maybe gone. From your perspective, it was just a year. But for Earth, you jumped through time, skipped ahead. Your own clock, your heartbeat, your aging, all of it slowed down so much that you moved into the future without feeling a thing. It's wild, isn't it? Here's another way to see it. Picture everyone on Earth watching the same movie in real time, and you, moving near light speed, you're watching that same movie in slow motion. The longer you watch, the further you drift out of sync, until by the time their movie ends, you're still halfway through. That's time dilation. Your time stretching, the universe's time racing. And it's not just speed that does it, gravity does too, and in a way you might not expect. Einstein figured that out in his other masterpiece, general relativity. Gravity, he said, isn't really a force pulling on you, it's the warping of space-time itself. The more massive something is, like a planet, or a star, or a black hole, the more it bends that fabric, and the closer you are, the slower time moves for you. It's called gravitational time dilation, and it's one of the strangest, most beautiful ideas in physics. You can see it play out perfectly in that scene from Interstellar. The crew flies toward this enormous black hole called Gargantua, and they land on a planet orbiting right next to it, so close that space and time are being stretched to the limit. Down there, an hour equals 7 years back on Earth. 7 years. It sounds impossible, but that's what gravity can do. It bends reality. And when they finally get back to the ship, only a few hours have passed for them, but the man who stayed behind, he's aged 23 years. He's older, tired, a lifetime heavier, because time for him ran faster. That's not fantasy, that's Einstein's universe. The closer you fall towards something massive, the more space-time itself stretches, and your seconds, your minutes, they slow, they drag, they almost stop. Near a black hole, time doesn't just move differently, it nearly stands still. So here's the thing, Christopher Nolan, the director, he didn't just invent this for the drama, for the spectacle. No, the whole idea of gravitational time dilation near a black hole, that's real physics. That's Einstein's general relativity in action. And the film Interstellar, it had someone making sure of that. Kip Thorne, a theoretical physicist, Nobel laureate, one of the sharpest minds alive, he was there as the scientific guide. He worked with Nolan to make sure Gargantua, that giant spinning black hole, and the way time behaved around it, were as close to reality as possible. Because according to Thorne's equations, time really does stretch near something that massive. It really does slow down. The movie made it visual, but the truth is already stranger than fiction. And you don't even need a black hole to see it. We can measure time dilation right here on Earth. Back in the 1970 seconds, scientists tried it, two atomic clocks, the most precise we could make, one left at sea level, the other carried up to a mountain about 2,300 meters high. They let them tick for 11 days and then compared them. And sure enough, the clock on the mountain was ahead, just a fraction, but ahead. Time had moved faster up there. Why? Because gravity. The higher you go, the weaker Earth's gravity becomes, the less it curves space-time, and the faster time runs. Down at sea level, closer to Earth's mass, time drags ever so slightly. The difference was tiny, a few billionths of a second, but it was there, measurable, real. So even here in the quiet of our planet, relativity whispers in the background, bending seconds. And then there's something else, something wilder, the idea of a warp bubble. In 1994, a physicist named Miguel Alcubierre proposed it. A theoretical drive that could, in principle, let you cross the stars faster than light without actually breaking any laws of physics. Using the math of general relativity, he showed that if you shaped space-time just right, if you adjusted the metric itself, you could make a region where space moves, not the ship. Inside that bubble, time would feel normal. Outside, the bubble could sweep across light years in what felt like moments. It's such a strange idea, right? Because we always think of travel as pushing through space like a car on a road. But in Einstein's universe, space and time aren't just the road, they are the thing itself, a flexible fabric that bends and ripples. So what if instead of moving through space, you move the space around you? Alcubierre imagined contracting space in front of the ship, expanding it behind, and the bubble just rides that wave. The ship itself never moves locally, but the bubble, the patch of space it's sitting in, it surfs across the cosmos. And because it's the space that's moving, not the ship, it could, in theory, travel faster than light without tearing physics apart. It's wild, it's almost poetic, like surfing the universe itself. Imagine this for a second, right? Grabbing space-time itself, not just moving through it, but reshaping it, bending the fabric of the universe so it carries you across vast distances and maybe even through time. It's not really about going faster than light, not exactly. It's about stepping into the future itself. Here's how it works, at least in theory. Inside a warp bubble, time doesn't behave the way it does outside. For you, inside, maybe only a few months, maybe a year passes, but outside, entire centuries could slip by. So you could leave Earth in the year 2100, spend what feels like a single year traveling, and arrive at another star to find that the calendar back home now reads 3100. You would have jumped 1,000 years ahead while aging only one yourself. And the strangest part, the passengers wouldn't even feel it. They wouldn't be speeding through space in the normal sense. There'd be no violent acceleration, no crushing G-forces, no blinding streaks of light, just stillness, calm, as the universe outside rushed past at impossible speeds. That's because the ship itself wouldn't be moving, really. Space would be moving around it. But to make that happen, you'd need something exotic, something we've never truly seen, a kind of energy that acts the opposite of everything we know. Negative energy. It would have to generate repulsive gravity, pushing instead of pulling, stretching instead of compressing. We know, in theory, it can exist in tiny flickers inside quantum fields. Like in the Casimir effect, when two metal plates in a vacuum attract because the vacuum between them isn't truly empty. But we've never been able to gather that energy, not in any usable amount. Still, the idea is serious enough that NASA's Eagle Works laboratory explored it. Dr. Harold Sonny White proposed adjustments to the original model that could, at least mathematically, reduce the impossible energy demands. Instead of needing the energy of a planet like Jupiter, his version suggested maybe the mass of a car, still far beyond us but less absurd than before. Of course, the obstacles are enormous. To shape space-time like that would mean manipulating it on scales we can't even approach. And even if we could form the bubble, keeping it stable would be another nightmare. Theoretical models suggest it could fill with deadly radiation, and if the bubble ever collapsed, it might release that energy in a burst powerful enough to obliterate everything nearby. But even with all that, the Alcubierre drive, as it's called, is fascinating because it doesn't break physics. It lives entirely inside Einstein's general relativity. It's not forbidden, just unreachable for now. And then there's another idea, one even stranger, something called a white hole. If a black hole devours everything, letting nothing escape, a white hole would be its mirror image, an object that refuses to let anything in, instead blasting matter and energy outward like a cosmic fountain. The concept actually falls straight out of Einstein's equations, because if you flip the math for a black hole, you get a solution that looks like its inverse, a door that only opens one way. You can't enter it because it's constantly throwing everything out. Now, here's where it gets really weird. Some physicists think a white hole might be connected to a black hole through a tunnel in space-time, a wormhole. Picture that, falling into a black hole, surviving somehow the gravity that would crush almost anything, and then emerging somewhere else entirely through a white hole. And because of the way time stretches and bends inside those regions, you might crawl out far, far into the future compared to when you began. 1,000 years, 1,000,000, who knows? You wouldn't just travel through space. You'd be stepping through the geometry of time itself. Imagine this for a second. You step into a black hole in the year 2025, and somehow impossibly you come out of a white hole in the year 4025. From your point of view, maybe only a few minutes pass, maybe an hour, but back on Earth, 1,000 years have slipped away. And that's the thing, right? Because in theory, a white hole could act like a one-way time machine, a door that only opens forward, never back. It would launch you into the future and never let you return. The strange part, though, is that white holes are still just math, just theory. We know black holes are real. We've seen them, photographed them, like that famous shadow in galaxy M87. But white holes, no one has ever found one, not yet. Some scientists think they might exist only in the most extreme conditions, maybe as relics from the first moments after the Big Bang, frozen echoes of creation. Others say no, they're just artifacts of equations, possible on paper but impossible in nature. Still, the idea lingers because it's too strange to ignore. There are theories that try to tie them to the mysteries we already see out there. Those sudden flashes of energy called gamma ray bursts. Some believe they might be white holes firing off their last breath of light. But we don't know. No proof. Not yet. And yet the thought itself is wild. If white holes did exist, if somehow we could find one and not be ripped apart by the gravity near it, we might ride it like a cannon across time, shot into the far future, a shortcut through the fabric of space-time itself, a cosmic tunnel, a slingshot, a way to cheat the clock. And there's another way to reach the future, not through stars or singularities, but through stillness. You just stop, you freeze yourself, and wait. It sounds absurd, right? But that's cryonics, and people have actually done it. The idea is simple but impossible at the same time. If you could stop every chemical reaction in your body without killing yourself, you could pause life, drift through the centuries like a sleeping traveler waiting for the world to catch up. When you wake, the world could be unrecognizable, diseases cured, aging defeated, ships sailing between galaxies. You'd open your eyes to the future, unchanged, the same person in a new age. And it's not fantasy. Cryonics companies exist right now. When someone dies legally, they rush to cool the body down with liquid nitrogen to about minus 196 degrees Celsius. Everything freezes in place, every neuron, every cell, locked in time. Then you wait. The most famous is James Bedford, a professor who died in 1967. He was the first to be frozen, and he's still there now, suspended in a metal chamber, waiting. Others have followed, some preserving the whole body, others just the head, betting that one day future science will know how to rebuild the rest. But the truth is, we can't bring anyone back. Not yet. Ice crystals tear cells apart. Chemicals meant to protect them can damage them. Even if the body survives the cold, the thawing is the hardest part. No one has done it. So cryonics really is a lottery ticket to the future. You pay now and hope that someone someday will figure it out. But if they do, if it ever works, it's time travel of a very different kind. You're not moving faster through time. You're stopping completely while time races ahead. Imagine closing your eyes in 2025 and opening them in 2500. For you, no time has passed. One moment here, the next. A new world. That's not fiction, that's physics, waiting for a miracle. And that's what makes it so human. Cryonics isn't a machine, it's a promise. It's a quiet faith that science and curiosity and maybe luck will carry you forward. Of all the ways we've imagined reaching tomorrow, this is the only one people are truly trying today. It's not about escaping death. It's about believing that the future will remember you, that it will be kind enough, brilliant enough to bring you back. So skipping forward in time is already hard enough, right? But what about the other way? What if you could rewind the clock, actually go back, see the past unfold again with your own eyes? It sounds impossible, completely absurd. But when you start digging deep into physics, into the strange logic of space-time, you find whispers, hints that maybe it's not entirely out of reach. You know that moment in Back to the Future when Marty McFly hits 88 miles per hour in the DeLorean, the lights explode, the car ignites in streaks of fire, and in a blink, he's torn out of 1985 and dropped into 1955. It's one of those scenes that sticks with you because it makes time travel feel almost casual, like it's just another form of motion. Just hit the right speed and boom, you're gone. But of course that's fiction. It's beautiful, it's thrilling, but it's fantasy. Still, the idea underneath it, that dream of stepping backward through time, has haunted physicists for decades. Could time be navigated the same way we move through space? Could there be a real path, a route through the geometry of the universe that lets you go not only forward but back? According to Einstein's general relativity, it's not completely forbidden. In fact, the same mathematics that explains gravity, that describes black holes, also leaves room for some truly wild possibilities. One of them is the wormhole, a kind of hidden tunnel through space-time, connecting not just distant points in space, but maybe distant moments in time as well. If Back to the Future made time travel look easy, Interstellar tried to make it real. And that's where things get fascinating. Remember that scene where Cooper and his crew land on the water planet near the black hole Gargantua? Time moves differently there. Hours on that surface equal decades for those waiting farther away. By the time they return, their friend has aged a lifetime, while they've barely aged at all. Cooper didn't use a time machine, he didn't need one. Gravity did the work. That's time dilation, pure relativity in action. But later, when Cooper falls into Gargantua, something even stranger happens. He doesn't die, he doesn't get crushed. Instead, he finds himself inside something like a higher dimensional space, the Tesseract, where every moment in his daughter's bedroom exists at once. Past, present, future, all stacked together like layers in a deck of cards, all visible at the same time, in that place. Time isn't flowing anymore, it's laid out. Cooper isn't just watching it, he's interacting with it, shaping it, sending messages back that had always been there. That's the strange beauty of it. He doesn't create a paradox or split the timeline. Everything he does was always part of what happened. He was always the one knocking those books, sending those codes. He just didn't know it until he was inside. And that idea, that loop of cause and effect folded back on itself, that's something physicists actually talk about. It's called a closed time-like curve, a kind of mathematical loop where time bends so far it meets itself. It sounds impossible, but it doesn't break the rules. It just rewrites what we mean by before and after. The future and the past, woven together, consistent, connected, one long thread looping through the universe. So Cooper's actions inside the Tesseract, they show us something strange, something kind of beautiful actually, a version of time travel that doesn't tear the timeline apart but completes it. He didn't step backward into the past in a physical sense. He didn't walk through it, but he reached across it, he touched it from within the structure of time itself. He changed what was always meant to happen, not by breaking causality, but by fulfilling it. And that idea, that time, could allow itself to be shaped from within. That's wild, isn't it? But then you start to wonder, could full travel, real movement, your entire body shifting backward through time, ever be possible? And the surprising answer, according to physics, is yes, at least in theory, through something called a wormhole. A wormhole is like a shortcut through space-time. Instead of crawling across the stretched, flat surface of space for light years, you could slip through a tunnel, vanish from one region, and emerge somewhere else, or maybe somewhere else. Imagine the universe as a giant sheet of paper. Normally, if you wanted to cross it, you'd have to move along the surface one point to another, the long way. But what if you folded the sheet, bent it until two distant points touched, and then poked a hole straight through? Suddenly distance disappears. You could jump across in an instant. That's the essence of a wormhole. Physicists call it an Einstein-Rosen bridge, a mathematical solution to Einstein's field equations, a bridge connecting two regions of space-time. And depending on how it's arranged, it might allow movement not just across space, but through time itself. Now here's where it gets really strange. If one end of the wormhole moves differently through time than the other, then the bridge could become a real time machine. Enter one mouth and come out of the other, not just somewhere else, but someone else, maybe in the future, maybe in the past. One way to do this would be to drag one mouth near the speed of light, like hauling one end of a tunnel on a ship racing through space. Because of special relativity, time slows for the moving end. When the two mouths reunite, they're no longer synchronized. Walk into the stationary mouth and you could emerge from the moving 1 year earlier, or reverse it and step into the future. Which direction you travel depends entirely on how the two mouths are treated. If the moving one spends time near a black hole or travels at high velocity, it will experience less time. It will be younger. So passing from the older end to the younger end sends you backward. Going the other way sends you forward. Think of it like an escalator, one side running faster, one slower. Step one way and you rise ahead, step the other and you fall behind. In a wormhole, the same logic applies. Step through one way and you might find yourself in yesterday, the other way tomorrow. But there's a limit. You can only go back as far as the wormhole's creation. You can't visit the dinosaurs unless that tunnel has existed since their age. Most of the stories we tell about time travel, they focus on moving forward, maybe because it feels safer, cleaner. But going backward, that's where things get messy, unpredictable, fascinating. Wormholes could, at least on paper, let you meet your own past. You could, in theory, stand face to face with your younger self, and yet that comes with enormous problems. The biggest is stability. Wormholes wouldn't stay open on their own. Gravity would crush them shut. To hold one open, you'd need something extraordinary, a kind of exotic matter, stuff with negative energy density, the opposite of normal mass, something that pushes outward against gravity instead of pulling in. It would have to resist collapse to prop the tunnel open against the universe's instinct to close. And that's the thing about wormholes, about time travel in general. It's not just about defying physics. It's about asking whether the universe itself would even allow us to see it from both sides at once. No one's ever found exotic matter, not yet, but physics says it could exist. It's allowed, at least in the math. Quantum effects show that negative energy can happen fleetingly, momentarily, tiny blips of it appearing and vanishing. The question is whether it can exist in the right amount, in a way that's stable, usable, something you could actually harness. And that's the catch, because if you wanted to hold open a wormhole, you'd need it. You'd need that strange negative energy to keep the tunnel from collapsing. Even the smallest disturbance, a flash of radiation, a passing particle, the tiniest ripple of gravity could make it snap shut before anyone got through. And if it did, if the wormhole pinched closed while you were halfway inside, well, that wouldn't end well. But even if you could keep it stable, there's another problem that creeps in, and it's not mechanical, it's logical. Paradoxes. If you could go back through time using a wormhole, you might stop your grandparents from meeting, or send yourself a message that changes your own past decisions. Reality doesn't like that. Still, general relativity doesn't forbid it. The equations actually allow for something called closed time-like curves, paths that loop back on themselves. They're built right into the geometry of space-time. It means that under extreme conditions, the universe itself might permit travel into the past without tearing everything apart. Kip Thorne, the physicist who worked on the film Interstellar, explored this deeply. He showed that if you had the technology to manipulate a wormhole, you could, in principle, build a time machine that obeys the laws of physics. The problem, again, is scale. The energy and precision required are far beyond anything humanity can manage right now. But the math still whispers, it's possible. And then there's another twist. You don't even need a wormhole. Einstein's equations themselves contain the seeds of time loops. They're called closed time-like curves, or CTCs, and they're even stranger. Imagine time not as a straight arrow, but as a loop bending back into itself, so that if you followed the curve far enough, you'd arrive not somewhere else, but somewhere else, a moment that already happened. It's like walking forward only to find yourself back at the beginning. The idea came from the mathematician Kurt Gödel in the 1940 seconds. He found a solution to Einstein's field equations, one that described a universe rotating as a whole. In that kind of universe, space-time twists so much that paths can close in on themselves. They don't go off to infinity, they come back. So an object or a person could travel through space and end up in the very moment they started, carrying the memory of having moved through time. It doesn't break relativity, it fits it perfectly. But it does open doors to paradoxes, the same ones that make physicists uneasy. The grandfather paradox, the self-creation loops, all those tangled possibilities. For a CTC to exist, space-time itself must be unbelievably curved, warped by rotation or immense gravity, maybe near something like a Kerr black hole, one of those spinning monsters that drag space and time around with them. In theory, if you entered one of those, followed its curves precisely, you could loop back to a time before you even crossed the horizon. No one has seen it happen, of course. It's theory, elegant and unsettling, but time travel, maybe it doesn't need massive black holes or cosmic tunnels at all. Maybe the clue is hiding somewhere smaller, in the quiet quantum world, where particles flicker, disappear, reappear, and sometimes for reasons we barely understand seem to ignore time altogether. They can do things that really shouldn't be possible, right? They can pop in and out of existence like ghosts, act like waves, and somehow be in two places at once. And the wildest part, the bit that still makes my brain stutter, is that they can borrow energy they don't even have, just for a blink, as long as they pay it back fast enough. It's like reality gives them a short loan, a cosmic credit card, and says fine, but don't keep it. And that tiny loophole lets them do things they absolutely shouldn't, like tunneling through walls, or maybe even skipping backward through time for the briefest instant. This isn't science fiction. It comes straight from quantum field theory, which merges Einstein's special relativity with quantum mechanics. In that framework, scientists draw these strange, elegant sketches called Feynman diagrams. Each line, each arrow, is a story about how particles move, meet, or transform. And sometimes, something remarkable shows up. A particle traveling backward through time looks identical to its opposite, its antimatter twin, moving forward. A positron, for example, can be seen as an electron running the film of the universe in reverse. Then there's quantum tunneling, an actual thing we've measured, where particles don't break a wall, they just appear on the other side, as if the universe itself briefly forgot the rules. Some interpretations say they're not really breaking through, they're taking a shortcut, slipping through a fold in space-time, bending the ordinary flow of cause and effect. It's not quite time travel, but it feels dangerously close. The particle ends up where it shouldn't be, faster than it should, like it cheated time, like it knew the future before it got there. But the trick only works at the smallest scales imaginable. Try stretching it up to something bigger, even a speck of dust, and the illusion shatters. The laws snap back. Time returns to its steady march forward, unbroken. Still, every time we talk about going back, We hit the same wall, the same impossible knot. Paradoxes. The most famous is the grandfather paradox. Picture it. You build a time machine, travel back to when your grandfather was young, and by accident you stop him from meeting your grandmother. Maybe you distract him, maybe he just never makes it to that date. If they never meet, your parent is never born. And if your parent is never born, you're never born. But then who went back to cause it? It's a loop that collapses on itself. Physicists have wrestled with that puzzle for decades, trying to save the dream of time travel without tearing logic apart. One escape hatch comes from quantum mechanics, the many worlds interpretation. In that view, every decision, every action, every measurement creates a new branch of reality. So if you go back and stop your grandfather, you don't erase your timeline, you just make another one, a copy, where you never exist, while your original world carries on untouched. It's like copying a file on your computer. You don't delete the first one, you just create a new version. Clean, neat, elegant even. But it comes with a catch. You can't actually change your own past. You can't undo loss or rewrite what's already written. You can only make another universe where things are different, while your own remains exactly the same. And even that doesn't solve everything. There's another paradox, one that's somehow even stranger. The bootstrap paradox. Imagine this. You travel back with a copy of Beethoven's symphonies, hand them to young Beethoven, and he writes them down, becomes famous for them. But where did the music come from? You got it from him, but he got it from you. There's no origin, no first spark. The music just loops through time, forever self-created. Cause and effect folded in on themselves. It's like standing between two mirrors, reflections stretching into infinity, and you can't tell which one began the pattern. It's beautiful, but it's deeply unsettling, because it means maybe not everything has a beginning. Maybe some things just are looping endlessly, written into the geometry of time itself. Scientists still haven't found a satisfying answer for this one. It's one of those questions that just won't sit still. Some think maybe those closed loops, those strange cycles of cause and effect, are just how the universe works, if time travel is possible at all. Others say no, those paradoxes, those impossible loops, they're proof that true backward travel can't happen, that the universe simply won't allow it. And then there's the predestination paradox, which is, well, it's even stranger. What if everything you do to change the past actually makes it happen? Imagine this. You hear about a disaster in the future, something terrible, so you build a time machine to stop it. You go back, determined to change everything, but when you arrive, you make a mistake, something small, something you don't even notice, and that mistake becomes the reason it happens. You weren't the hero, you were the cause. You were the spark that lit the fire you came to prevent. And that's the part that gets you right. Because stories love this kind of trap. In 12 Monkeys, Bruce Willis's character thinks he can stop a virus outbreak, but everything he does just locks the future into place. In The Terminator, they try to stop the rise of machines, but in doing so, they create the very future they feared. Even in Harry Potter, when Harry cast the spell he thought came from someone else, it's him all along. Every paradox turns into a mirror, showing us something we don't want to see, that maybe the past is more fixed than we imagine. Because even if the math itself allows it, maybe the universe is built with safeguards, soft barriers that stop you from changing anything that truly matters. Maybe history is like wet cement. You can press your hand into it, leave a mark, but you can't reshape the whole path. Or maybe, if the multiverse is real, every trip backward just splits the road, creates another branch, another version, while the one you came from keeps going untouched. Infinite worlds, blooming with every choice. And yet, none of them give us peace. Every theory just opens more questions. Every answer cracks under its own weight. Time travel keeps slipping through our fingers like water, refusing to behave. It feels impossible, and maybe it should. Paradoxes leap out from every corner, waiting to twist logic into knots. It's like trying to unmix paint to unscramble an egg. The universe doesn't seem built for it, but still, you can't help wondering, can you? What if we take every wild idea we've ever had, every theory, every equation, and stitch them together, something vast enough, bold enough to bend time itself. And if we do that, well, we start with the heart of it, the power source. Because moving through time, that's not like driving down a road. You're not just moving across space. You're pulling at the fabric of space-time, trying to fold it, twist it, push through it. And that takes energy, not just a lot, but an impossible amount, more than humanity has ever dreamed of controlling. When physicists went looking for something in nature powerful enough to do it, one thing stood out, one monster among the stars, the black hole. But not just any kind, a rotating one, a Kerr black hole, named after Roy Kerr, who found the solution back in 1963. This thing doesn't just sit there like a cosmic drain. It spins almost at the speed of light. And when something that massive spins, it drags space itself around with it, twisting reality into a storm. It's called frame dragging. Picture it like a tornado made of gravity. If you could get close enough, somehow survive the pull, you might ride that swirl, loop through time itself. Inside a region near it, the ergosphere, space-time twists so violently that going forward the normal way isn't the only path left. Pick the right orbit, the right motion, and in theory you could fall back into your own past. The black hole becomes a kind of cosmic dynamo, a generator of tangled time. But trying to tap into that, trying to ride that power, would be like plugging your phone into a tornado and hoping lightning hits. It's madness. Beautiful, impossible madness. The thing about black holes, it's just wild, right? The energy near that edge, the event horizon, is so extreme that no known material, nothing we've ever made or imagined, could survive there. It's pure chaos. And if you wanted to use that power, you'd have to reach into the accretion disk, that glowing hurricane of gas and dust spinning around the hole at nearly the speed of light. In our version, though, in this thought experiment, we picture a massive station orbiting at just the right distance, balanced between destruction and stability. Giant magnetic fields reach out and pull energy from those plasma streams, turning disorder into usable power. But energy alone, that's not enough. You can't just have raw power. You need a way to shape it, to sculpt the very geometry of reality into a path through time. That's where the space-time ring comes in. Imagine stirring a bowl of thick honey. At first it just swirls, lazy circles, but keep stirring faster and faster. And the center starts to dip, to fold in on itself, little spirals forming out of the motion. That's what we'd be doing, but with space-time itself, spinning it so violently with mass and energy that it folds over and connects to itself, forming closed loops in time. Physicists call them closed time-like curves. The idea isn't fantasy. It's rooted in real equations. First imagined by Frank Tipler back in 1974, he built on an earlier concept from Willem van Stockham. The idea was this: take an infinitely long cylinder made of ultra-dense matter, spin it almost at the speed of light, and around it space-time would twist so tightly that time itself would bend back, looping into the past. But there's a catch. Infinity doesn't fit inside our universe. We can't build a structure that never ends. So any real attempt would have to be finite, and that breaks the neat perfection of the math. A finite cylinder wouldn't hold its loops cleanly. It would need help, exotic matter maybe, or engineering precision beyond anything we can dream of now. In our version, we imagine a glowing ring instead, massive but not endless, spinning so fast it drags space-time around with it. It would blaze with energy, like a halo made of starlight, a wheel turning at unimaginable speed. Keeping it stable would require materials tougher than any metal we know, maybe something forged from exotic states of matter, or those hypothetical cosmic strings, thinner than an atom but heavier than a mountain. Maybe one day, because that ring, that structure, it's the scaffold we'd need to shape the river of time itself. But even then, even with that impossible ring, we're not done. You still need a road, a passage through the twisted geometry, and that's where wormholes come in. Wormholes, Einstein-Rosen bridges, shortcuts through space-time. They fall naturally out of general relativity, but the problem is they collapse almost instantly. They snap shut before you can cross. To keep one open, you need exotic matter, something with negative energy density. That sounds made up, but maybe it isn't. There's this experiment, the Casimir effect. Take two metal plates, put them extremely close together in a vacuum, and they actually pull toward each other, not because of gravity or magnetism, but because the energy between them drops below zero. Negative energy, tiny but real. It's not the same thing we'd need to hold a wormhole open, but it's a hint, a whisper that the universe might allow it. If we could generate enough of it, harvest or stabilize it, maybe we could widen a wormhole's throat, make it solid enough for a ship or a person to pass through safely. But then there's the question of navigation. How do you know where or when you're going? On Earth, we use GPS, satellites sending out time signals, our phones triangulating position from delays in the signal. But time travel breaks all that. Everything's moving. Earth spins, it orbits the sun circles the galaxy, and the galaxy itself is drifting through the cosmos. Step just a few minutes forward or backward without recalculating, and you might appear in empty space, the planet already gone from that coordinate. The solution might be quantum entanglement. Entangled particles stay connected no matter how far apart they drift. If we could entangle clocks or particles at fixed space-time coordinates, they could act as anchors, tethering travelers to both a location and a moment, giving them a way home through the storm. Anton Zeilinger's work on quantum teleportation and Yane Pan's experiments with quantum satellites, they've done something extraordinary. They've shown that entanglement, that eerie link between particles, can survive across huge distances, not just in a lab, but between the Earth and space itself. And that's wild, because it means, in principle, the universe is already connected by invisible threads. Maybe someday those quantum entangled networks could become something more, something like an ultimate map for time travelers, a web of unbreakable beacons stretching quietly across the cosmos. Imagine it a kind of GPS for time, but instead of satellites, it's particles woven into the very fabric of space-time, whispering to each other across ages and light years, saying, "I'm still here. You still remember." Building a time machine, even on paper, feels almost impossible, like trying to assemble a jigsaw puzzle made of pieces from different worlds, pieces that shouldn't even fit together. You need the unstoppable pull of a rotating black hole, the kind that bends not just space but time itself. You need materials that shouldn't exist, exotic matter, negative energy, things that twist physics into knots. You'd need quantum precision, entangled particles guiding your path through the folds of reality, and a little hope that the universe doesn't swat you out of existence for trying. Each part of that recipe is already miraculous on its own, and putting them all together, well, that feels like asking the universe for a miracle stacked on top of another. And yet, here's the beautiful thing, the equations, the theories. They don't say no, they whisper maybe. They leave a door slightly open, just enough for imagination, innovation, and maybe one day creation to slip through. If future civilizations ever learn to harness the energy of stars, if they can master the geometry of space-time itself, if they can tame quantum strangeness the way we use electricity, then maybe they'll build machines that can ride the current of time. Machines so advanced they'd look like magic to us. And maybe that's why we haven't met any time travelers yet. Maybe it's not forbidden, just too hard, too costly, too dangerous. Or maybe they built them and vanished into other timelines. Or maybe they saw what could go wrong and buried the idea forever. Still, chasing it matters. Because in trying to understand time, we're forced to push every limit we have in physics, in engineering, in imagination. We ask bigger questions. We dream larger dreams. That's what science really is, not just rockets or lasers or equations. It's the reach, the act of stretching toward the impossible, of trying to touch the stars or, in this case, the river of time itself. Even knowing we'll probably fall, we reach anyway. Because maybe somewhere hidden in the tangle of black holes and quantum paradoxes, there's an answer waiting. Or maybe not an answer, but a better question. So when someone says time travel is impossible, you can smile and say, maybe for now. Because the universe is vast and strange and full of surprises. And if history tells us anything, it's that humans have a way of turning impossible things into reality. Given enough time, we might stop dreaming about time machines and finally step inside one. Um, so here we are again, right at the edge, where thought begins to blur, where the noise of the world softens, where everything that used to feel far away starts to fold closer. You've been traveling through stars and theories and impossibilities for a long while now, and maybe without even noticing it, you've drifted back to this small, still point. The place where all those questions about time and light and gravity dissolve into something quieter. The universe has been talking all this time, you know, not in words, not in equations, but in the soft rhythm of being itself. And if you listen carefully beneath the hum of your own thoughts, you can almost hear it breathing with you. It's strange, isn't it, to realize that silence is not emptiness but fullness. Every pause, every heartbeat, every space between thoughts is the universe resting. You are resting with it. For billions of years it has been expanding and cooling and blooming, and yet here it is, here you are, part of that same unfolding. The atoms that make your heartbeat once shivered inside stars. The light that touches your skin tonight has been traveling for ages just to arrive here, in this moment, with you. You don't have to hold any of it. Just let it be. Feel the air move slowly in and out, the body remembering how to trust gravity, how to sink back into the bed of the cosmos. You know, it's funny, we spend so much time trying to understand the universe, chasing its edges, measuring its speed, naming its forces, and yet sometimes the most honest understanding comes when we finally stop measuring, when we simply listen. Because in listening, we become part of the story again. The universe isn't out there. It's right here. It's in the warmth behind your eyelids, in the slow pulse of your wrist, in the way your mind drifts between memory and imagination, like a comet crossing between worlds. You can let that drift happen now. There's nowhere else to go. The galaxies will keep spinning without you having to push them. The stars will burn quietly while you sleep. Everything is taking care of itself, and that's the miracle. Somewhere far beyond, cosmic winds move through dust clouds, new stars are being born, light bends and folds and breaks into color, and yet all that vastness, fits gently within this breath you're taking. The same physics that guides galaxies guides your heartbeat. The same gravity that curves space-time cradles you now, draws you softly into rest. You are being held by laws older than words, by patterns deeper than memory. You don't have to understand them tonight. You don't have to solve anything. Just let the understanding sink beneath thought into that quiet part of you that already knows, the part that existed before language, before time, the part that hums like starlight. Maybe you can feel it now, that slight shimmer beneath everything, the sense that existence itself is exhaling. It's the same stillness that the early universe must have felt right after the first light appeared, that moment when everything was new and infinite and calm. You carry that calm within you. It's in your cells, in your bones, in every photon of your body's light. The cosmos isn't distant, it's intimate. It's the pulse behind your thoughts. And maybe, just maybe, that's what it's been trying to tell us all along. That there's no real separation between knowing and resting, between science and silence, between looking out and falling inward. They're the same motion, the same surrender. So if your eyes are starting to close, that's all right. Let them. You're not missing anything. The story keeps unfolding whether you're awake to watch it or not. Because sleep too is part of the universe thinking, dreaming through you. The galaxies have their own kind of sleep, the long, slow rest between bursts of light. Planets too rest in their orbits, carried by gravity's invisible embrace. Everything in creation has its rhythm of waking and sleeping, and tonight you are simply joining that rhythm again. So let it happen. Let the thoughts drift, like dust in a sunbeam, scattering, shining, fading. There's nothing you need to hold on to now. The questions can wait, the stars will keep, the light will still be there when you wake. And as you breathe, Maybe you can feel the air settling around you, the molecules that have traveled through forests and oceans, and the lungs of countless creatures now moving quietly in and out of you. You are part of that endless exchange, the invisible rhythm that links all living things. Every breath you take is the universe whispering through you, and every exhale is you whispering back. It's such a simple thing, breathing, but in its simplicity there's something sacred. You are not separate from the vastness, you are its continuation, its soft echo. You don't have to do anything to deserve that. You've already arrived. Maybe you can feel your heartbeat now, steady, unhurried, like the quiet ticking of a cosmic clock, marking not the passage of time, but the pulse of existence itself. Each beat is a ripple, spreading through space-time, gentle but real. Your personal, gravitational wave. If you could listen closely enough, if you had instruments sensitive beyond imagination, you'd find that the whole universe vibrates together, faintly, endlessly, like a great ocean of energy breathing in unison. The stars, the atoms, the dark matter that holds galaxies in their invisible hands, all of it humming on frequencies too subtle for us to hear, yet somehow we feel it. Maybe that's why the night feels so alive, even when it's quiet. Maybe that's why stillness feels so full. There's a kind of grace in that realization that the universe doesn't need to be loud to be profound. Its miracles happen in silence. Right now, while you lie there listening, hundreds of billions of stars are being born. Entire worlds are beginning. Somewhere, a nebula is glowing, and its light will take millions of years to reach anyone's eyes. But here, for you, tonight, it's all happening at once. The past, the present, the future, they're just different textures of the same eternal now. You don't need to reach for them. They're already inside you. The atoms that were once part of a dying star are now part of your body. The energy that once fueled an ancient sun is glowing softly behind your eyes. When you close them, you are looking back into that same cosmic fire. And maybe that's why dreams exist, to let us wander through the universe without moving, to remind us that imagination is just another form of travel. So as you begin to drift, you can let the edges of your thoughts blur. There's no need to hold the shape of anything. Let the mind open like a night sky. Let it expand until it's as wide as the horizon. Maybe you can even picture yourself floating through that sky, weightless, suspended in starlight, surrounded by constellations that don't need names. You don't have to guide yourself anymore. The gravity of peace will pull you exactly where you need to be. The same laws that spin galaxies are guiding your rest. The same quiet symmetry that governs the cosmos is arranging your dreams. And maybe somewhere in those dreams, you'll meet the parts of yourself that remember the beginning of everything, the moment when time and space first unfolded, the spark that set all this in motion. You'll remember not through thought, but through feeling, through the deep, wordless knowing that you've always been part of this dance. You always will be. The universe doesn't forget its stars, and it won't forget you. Every photon that leaves your skin joins the cosmic background, a faint but permanent trace of your existence. Even the smallest warmth you release becomes part of the story of light. You are woven into the record of everything that ever was, every sigh, every heartbeat, every whisper you've ever spoken. All of it is written into the fabric of reality, forever. Isn't that beautiful? The idea that nothing is truly lost, that even the quietest life leaves ripples that stretch into eternity. You don't have to understand how, just feel it. Feel the way the bed beneath you supports you, how gravity, this ancient invisible kindness, holds you in place. You're safe here. You're exactly where you're meant to be. The universe has been preparing this moment for billions of years, this one instant of stillness where you and infinity meet. There's nothing you need to do. No task, no worry, no unfinished thought. The stars will keep their places, the world will turn, the atoms will continue their quiet work, and you can rest. And now everything begins to slow, almost imperceptibly, like the surface of a lake returning to glass after the wind has passed. The thoughts that once flickered like stars begin to fade into a soft dusk of the mind. What remains is the hum beneath it all, the quiet pulse of existence that has always been there. You can feel it if you listen. A low luminous vibration in the space between your breaths, in the small silence that follows every heartbeat. It's the universe still speaking, but now in a language made of calm. The air feels heavier in the most beautiful way, as if gravity itself has turned kind, holding you instead of pulling you. You've traveled far tonight, through light and theory and dream, and you've seen how everything, even the most impossible thing, carries its own sort of peace. The galaxies do not rush. The stars do not struggle to shine. They simply are. And so are you. For the first time in a long while, you can let that be enough. The questions that used to burn at the edges of your mind can rest now. They'll still be there when morning comes. For now, the only truth that matters is this breath, this gentle pulse, this quiet awareness drifting on the tides of the cosmos. You might notice that your body feels lighter, as if you're slowly dissolving into the fabric of space itself, like mist in morning light. Your arms and legs, your chest, your thoughts, all of them easing outward, merging with the darkness around you until there is no clear boundary between where you end and the night begins. And that's the secret the universe keeps whispering. There are no real edges, only continuations. Every sound fades into silence. Every life returns to starlight. Every heartbeat becomes part of a larger rhythm. You are part of that rhythm now. The warmth you carry inside drifts outward, and the universe returns the favor, wrapping you in its vast, invisible embrace. Somewhere beyond, new worlds are being born, but here, in this small corner of infinity, all that's required of you is to rest, to surrender, not in defeat but in trust. Because the same forces that built galaxies are watching over you even now. They have always known your shape, they have always known your name. You can let go of the day, of the hours, of time itself. You are floating between seconds, and it's safe here. The cosmos doesn't hurry, it waits. It has waited billions of years for this breath of yours, this quiet meeting between consciousness and peace. So breathe. Let the inhalation draw in starlight. Let the exhalation carry away everything you no longer need. The body knows what to do. The universe knows what to do. And soon, the border between wakefulness and dreaming will blur until you can't tell one from the other. It will feel like drifting through the slow spiral of a galaxy, weightless, endless, free. Somewhere in that drift you might see flashes of light, echoes of memories, fragments of impossible places. Don't chase them. Let them move through you the way clouds move through sky. Every image, every color, every sound is just part of the night's language, speaking gently to the part of you that understands without needing words. This is what peace feels like. It isn't silence that erases, it's silence that holds. It holds every star, every dream, every small hope, without judgment, without end. And in this silence, the universe finally smiles back. It's been with you all along, hiding in the background radiation of your own heart, waiting for you to notice that it was never somewhere else. You were never alone. You were always home. So if your eyes are still open, you can let them close now. The darkness behind them isn't empty. It's filled with everything that ever loved you. Feel the weight of the blanket, the slow rhythm of your chest, the delicate gravity that keeps you tethered to this world just enough. And when sleep comes, let it take you gently, like a wave folding back into the sea. Dream wide, dream slow, dream deep. The stars will keep their watch, the earth will turn. The light will return when you wake. And if somehow you're still awake, still here with me at the edge of everything, tell me in the comments what held you, what thought, what wonder kept your eyes open. But if you've already drifted away, if the night has closed around you like soft wings, then good night, truly good night. May you rest in the same peace that moves through galaxies, in the same quiet that began the world. Sleep well, traveler of starlight. The universe is still breathing, and tonight it breathes with you.